Thanks everyone for joining in our Premise Plumbing Modeling Task Committee webinar today. Today's webinar is titled Operations in Premise Plumbing Systems. And we have 5 great speakers today. And as you can see on this slide, and Jason Kuntz is going to lead off the discussion with water management programs, an overview. And then we'll be followed by Jeremy Williams, then Patrick Gurian, and then Liliana Latonovich, and finally Tim Bartran. And I'll give a little introduction of each presenter right before they talk. So at this point, I'd like to have Jason, if you don't mind, with your presentation. Jason is a commander with the Environmental Health Officer Service at the Water, Food, and Environmental Health Services branch of the CDC, Center for Disease Control's National Center for Environmental Health. The Water, Food, and Environmental Health Services branch provides technical assistance, practice-based research, training, tools, and guidance to address environmental causes of foodborne and waterborne threats to health. Commander Kuntz leads the agency's environmental health component of preventing and responding to Legionnaire's disease. So with that, I'd like to turn it over to Jason, and thanks again, Jason.
Thank you. And I want to thank the American Society of Civil Engineers, Premise Plumbing Modeling Task Committee for the opportunity to present this morning. And I'll be giving a brief overview of water management programs, understanding that there are additional detailed resources that exist if you care to learn more. And I will preview a few of them during this presentation. So let's talk about events leading to Legionnaire's disease. Let's just set the stage a little bit before we dive into water management. So we have supply water, and we understand that supply water is not sterile, and small amounts of Legionella could make their way into a building water system, for example, and that's where the amplification can occur. And we're concerned about poorly maintained building water systems here. And so reviewing some of the basics for Legionella here, the optimal temperature is 77 to 108 degrees Fahrenheit. However, Legionella will grow outside of that range. We're also concerned about stagnation, scale and sediment, biofilm, protozoa, and of course, absence of disinfectant. And all of these need to exist at one time for Legionella to grow. And I always say that there's a few hallmarks to preventing Legionella amplification, and that is keeping cold water cold, keeping hot water hot, keeping water moving, and ensuring a disinfectant where appropriate. So we have that amplification within a building water system. We're then concerned about those aerosolizing devices. So the showers and faucets, the cooling towers, the hot tubs, and decorative fountains. We have to aerosolize the Legionella. And of course, the susceptible host who breathes in those aerosolized Legionella-laden particles, and a susceptible host, for example, weakened immune system, a current or previous smoker, just to name a few. So what do we know about source attribution? In 2016, we pulled a convenience sample, and that is our outbreaks that we have investigated in person. Occasionally, states or localities will request assistance from CDC to lead these outbreak investigations. So we looked at 27 building-associated outbreaks from 2000 to 2014. And what we're able to glean from this is we have common settings, and understanding that this is a convenience sample and not representative of all the outbreaks nationwide. So hotels were around half of what we investigated, and then long-term care facilities and hospitals, rounded out roughly the other half. The common sources, of course, are showers and faucets, cooling towers, hot tubs, and even industrial equipment. So oftentimes cooling towers or decorative fountains, for example, that may have an explosive outbreak resultant in many cases, may make the news. But but in reality, we oftentimes deal with potable water, Legionella contamination or cases associated with that. And what's notable about potable water or building water system Legionella growth and transmission is oftentimes, we'll see a case here, months may go by, we may see a case there. So looking a little bit deeper into that analysis, and that was in the form of an MMWR, which you see here on the screen. The big take-home point from that analysis was 9 out of 10 outbreaks were caused by problems preventable with more effective water management. And what we're seeing oftentimes is simple associated failures during these outbreaks. And as we break them down, or the root cause of these outbreaks, I guess is another way to say, environmental deficiency or failure, we break them down into process failures. Like, for example, management plan did not exist, or an inadequate one was in place, or a human error. A person did not perform something that they were supposed to do, such as checking maybe a thermostat on a water heater. Equipment repair, so equipment malfunctions, or unmanaged external change, which could be something like an unmitigated water main break that resulted in brown water entering the building. And 48% of these outbreaks were due to more than one of the above failures. Okay, so now we're transitioning into actual water management programs. So we quickly built the case, for water management programs, and that they can be helpful and reduce those common root causes that we see during outbreak investigations. So not all buildings require a water management program. So buildings that are recommended, of course, are healthcare facilities. Does your building primarily house people 65 years or older, like a retirement home or an assisted living facility? And this is a big one. Does your building have a centralized hot water system, like a hotel or high rise? So we know those water systems are more complicated, much more pipe, much higher likelihood or density of biofilm for that matter. Does your building have more than 10? And that one we get questions about a lot, but the reality of it is oftentimes these 10-story buildings have these centralized water systems. Or does your building have a device such as a cooling tower, a spa, or even a decorative fountain, or a centrally installed mister, such as those grocery store misters in the produce section? Those devices are recommended to have a water management program. You may have heard of the CDC Water Management Program Toolkit, or it's just, I think, called the CDC Legionella Toolkit, and there's a picture of it there on your screen. And that toolkit is actually a plain language version. So we translate the bedrock standard of water management, which is 180, into plain language to make it easier to digest for public health professionals, building managers, healthcare facilities, engineers, anybody responsible for implementing water management programs. And it's a step-by-step program which goes through all the aspects of water management and provides helpful examples, and including a healthcare specific section. That's freely and available online right there at the link. We also understand too that water management can be complex, especially in these large buildings. And oftentimes building owners and managers just need to know where to start. So we developed this training along with partners called Prevent LD, and it's a free training available at the link you see below. And it takes that CDC toolkit and ASHRAE 188 and puts it into a couple-hour training program. And it is free and available online. And I would like to point out some of the templates, and you can see just a brief screenshot of the template on the screen there. These are actually tools and templates that could form a water management program. And it concludes with 2 case studies, one of them in a non-traditional setting. It was an industrial setting, and the other one is in a long-term care facility. So I'd encourage you to take that if you want to learn more. Okay, here are the 7 steps roughly in water management. We don't have time to go into all of these in detail, so we'll touch on a few of them today. But I wanted to just kind of take you through these 7 steps briefly here. The first is establishing that water management program team. Then we're going to describe the building water systems using text and flow diagrams. And once we understand that water system and have that team established, we can then begin to identify areas where Legionella could grow and spread. Then we're going to put our control measures in place and discuss how we would monitor them. And then obviously we're going to establish ways to intervene when these control limits are not met. That's really critical, and we'll go into that more in a minute. And then make sure the program is running as designed and is effective. And of course, document and communicate all these activities. And this is an iterative, continuous process. So quickly there, those are essentially the 7 steps in water management. So we'll go into detail on a few of them here. So the most important is having a well-rounded water management team. And that team may change based upon the facility size, complexity, and type, such as healthcare. So we'll go through a healthcare example. We're going to need to have the ability to oversee the program, somebody in charge, somebody that can authorize expenditures or authorize things to be done, based on the water management program performance. We, of course, need knowledge of the water systems, and that's where facilities engineering and maintenance come into play. That also could be the role of a consultant, on the water management program team. And consultants play a critical role, where needed. However, a consultant should not be leading a water management program team. That should be given to, those daily responsibilities should be given to staff on site. And of course, we need people that can implement that water management program and then communicate regularly about it. And oftentimes in healthcare, we will see someone like an infection preventionist sit in on that water management team as well. Okay, so describe your building water system. This is where we're going to start to get into some of the engineering aspects of it. And ASHRAE 188 in the toolkit calls for first a simple text description of the water system. And what I mean by that is, okay, let's take a healthcare tower that has 3 independent hot water recirculating systems in it. Well, we would want to identify that in that text description. Tower A has 4 independent hot water recirculating systems set to 140 degrees at the water heater with a thermostatic mixing valves at point of use, and the hot water returns to the basement. And cold water is direct fed to various fixtures. So we need that text description to quickly understand that. Water management plan should be able to be picked up by somebody who is not familiar with the building and has a general understanding of how it is set up. And then we move into simple diagrams of the building water system. And this is critical here. And what you see is a simplified diagram here of what I think is probably a hotel here, because it's the pool and the hot tub. And we go through receiving to cold water distribution to heating to hot water distribution. So those two coupled together allow for someone to quickly understand that water system. And if you can't understand your water system, it's really difficult to implement a water management program. Okay, so now that we've understood our water system, we then can start to perform that hazard analysis, which I was describing earlier. Let's try to understand where Legionella may grow and potentially spread within your building water system. And this is going to be unique to every building. For example, the water heater temperatures may be different in this hotel due to limitations associated with equipment. So therefore, the hot water may be at more at risk associated in this hotel versus, another building. We also have a pool and a hot tub, in this building. And of course, a decorative fountain and a cooling tower. And then here, control measures and corrective actions. This is the process here where I think water management catches these environmental deficiencies that we find during these outbreak investigations. So let's use a hot tub here. So we have identified a hot tub, and our control measure is disinfectant within that hot tub, amongst other things, including cleaning and disinfecting, or cleaning it, of course. And that requires routine monitoring. And I am responsible for going out 4 times a day to monitor that hot tub's disinfectant levels. And if that disinfectant level is within those control limits, I mark yes, I record those results, and I come back and I do it again later. A bather load, could be something more complicated, such as a chlorinator that tripped or is broken. And then we're going to perform that corrective action, document those results, and it's within limits, yes. Then we'll continue back onto the old path. If it's not, we'll continue to work on it, and we may have enhanced monitoring. So that's the basics of control measures and corrective actions. So now we're sliding into the end of water management here, and that's the 2 V's, verification and validation. And verification is, are we doing what we said we should do? And that means, am I checking those disinfectant levels in that hot tub like I'm supposed to? And I should not be verifying that. Someone else should be verifying I'm doing those disinfectant checks. And then validation, is our program actually working to control Legionella? And that's where we're going to be reviewing our data to indicate, okay, looks like the maintenance and operation procedure we have in place is working for the hot tub. We're not routinely out of control limits. And that's also where Legionella sampling comes into play, which is an option to validate a water management program. And then in a healthcare setting, routine surveillance. can be used to validate the program. And last is continuous program review. As I indicated, it's an iterative process that's continuous, and we should update that water management plan based upon data, and it shows that control limits are outside or consistently outside, or we do things such as major maintenance or engineering changes within the building, or if cases are associated with the system. And that concludes my presentation.
Thank you very much, Jason. We're going to reserve questions for the end. So with that, I'd like to jump to our next speaker, which is Jeremy Williams. And as Jeremy shares his screen, I'll give a little introduction here. Jeremy is a licensed professional engineer and healthcare plumbing technical leader for USEPA. Jeremy has 15 years of experience using various modeling programs for the building construction industry. And Jeremy's going to talk about design industry building modeling practices. And with that, Jeremy, again, thank you very much for talking here.
All right, thank you, Rob. And thank you everybody in the task committee that's allowing me to speak today. We really do appreciate this committee and the work they do. From a design industry professional, we appreciate the information that we're getting from you guys, and we want to keep it coming. So I'm here today primarily to focus on how we use Autodesk Revit to gather information on the building's plumbing system. We then use that information to aid in plans for water management, as the previous speaker talked about. So we get into the current design industry. So just on the right here, this is a snapshot of what Revit has as far as inputs and calculations on a domestic hot water system, being water 120 degrees Fahrenheit, and then the conversion flow method is predominantly flush tanks. On the left here, we have output information for a domestic hot water system. This is where we find out that the volume of the system as a whole is 396 gallons, and total fixture units 279 fixture units, with a flow of about 81 GPM. So this is meant to illustrate the web of water piping within a commercial building. It's busy, but we'll drill down to clarify some of what you're seeing. We build the building virtually. The architect does it, builds the building itself, and we fill it with all the engineering, piping, ductwork, electrical. That's what we do as an industry. Getting down into just the plumbing side of things, this is a hot and cold water piping system of a 4-story building. This is a healthcare application. It has a basement and a penthouse, so you can see 1, 2, 3, 4 floors. The whole building volume is about 1,283 gallons, 887 gallons of cold water, 396 gallons of hot water. As we drill down a little bit more and we talk about flushing a water system out, we know that the water main has, from the street to the building, has 222 gallons. This requires flushing a drain valve 25 minutes at approximately 10 GPM to bring in fresh water to that drain valve location. From there, we want to flush out the common cold water riser. So coming into the building and going up to this hose bib up here. So the common water riser, 60 gallons, requires flushing a hose bib 12 minutes at approximately 5 GPM. Now we're going to focus a little bit on this 4th floor right here to get a little bit better clarity of what's going on. So this is a patient wing water isometric. This is a total of 20 patient rooms with all the ancillary common area, fixtures. So the patient wing volume is 220 gallons, with 150 gallons of that being cold water, 70 gallons hot water. Since we already flushed the cold, we want to look at this floor to flush the hot water common riser. So 27 gallons requires flushing a faucet 20 minutes at approximately 1.5 gallons per minute. From there, we flush the wing itself, so the mains in the wing. So the source is coming in over here. This is the most remote cold water fixture, the most remote hot water fixture. So approximately 100 gallons of cold and 55 gallons of hot requires flushing a faucet 70 minutes for cold and 40 minutes for hot at 1.5 GPM. As you can see, it can be a little time consuming when you're restricted to 1.5 GPM. From there, we drill down to just the patient room isometric. So this gets a little less volume, so 2.3 gallons on the cold, 0.7 gallons on the hot. So we got two faucets at 1.5 GPM each, requires 15 seconds of runtime each to flush out part of the main and the individual branch going to the fixtures. One shower at 2.5 GPM is 10 seconds of runtime just to clear out this main, or clear out the branches to the fixture itself. And then the water closet, one flush cycle clears out most of the rest of the main in this application. Other fixtures will vary depending on distance away from the flush main. So that's just a case by case. It's usually easier to figure out because you have one fixture coming off a main. So this slide is the sum of all the, this slide is the sum of all the data that I just showed. It shows it all in one slide. One thing I want to focus on is the fixture units is the sum of all the fixtures in the building. So that's what we, as a design industry, use to determine, flow rates. The flow GPM is based on the 2012 International Plumbing Code table in the USEPA. So that's just no consideration. It's basically Hunter's curve with no consideration of occupancy type. And then we get over here to the far right side, looking at the patient room. The 30 GPM is the instantaneous flow of a water closet. So at 1.6 gallons per flush, it's about 3.2 seconds of 30 GPM flow going to that fixture. So it's pretty rapid flow rate, but for a short period of time. And the other interesting bit of information is the IPC table comes out with 6.5 GPM with 3 fixture units, when in reality, the total connected fixtures is 5.5 GPM. That's assuming someone's taking a shower with nothing but hot water, someone's using the faucet inside that bathroom with nothing but hot water, and someone's outside in the patient room washing their hands with nothing but hot water. So it's interesting information that we get out of the system that isn't accurate. So we'll talk about the sizing impacts of industry standards. So right size versus industry size. I use the quotes as neither is clearly defined and need engineering judgment to implement. So when I talk about right sized, this is based on historical data collected via flow meter. Realistic diversities are taken on the flows, using that information from the flow meter that we've collected. We get the actual flows closer to 8 feet per second and on the cold water side and 5 feet per second on the hot water side. This does run the risk of undersizing and higher pressure loss. One of the anecdotes of the industry is no one complains about having too much hot water or too much water pressure. They always complain about the inverse of that. When we talk about industry size, it's based on Hunter's curve. This might consider diversities based on occupancy. The more experience you get, the more you realize that Hunter's curve is grossly oversized, but we don't know where to take it, to right size stuff. So unrealistic flows used in sizing, actual flows are far less than 8 feet per second on the cold and 5 feet per second on the hot. Actual numbers suggest reality at peak is less than 1 foot per second in large pipe. So the industry would always go with too large because you can always add to it, but we're realizing now that that's a negative impact on the building age of water. So I went on to apply industry standard sizings with no regard to realistic data to the model that I showed you. So we ended up with approximately a 30% increase in volume of water, more water to become stagnant inside pipes, lower velocities. The big changes were a 3-inch water main from the street becomes a 4. Most of the route increased by 1 pipe size. Individual fixtures or groups of fixtures are not impacted as they're already sized appropriately because there's no diversity you can take on those too much, because if a fixture's on, it's on. The other interesting piece of information we found was there's about a 40% increase in materials by weight. So in this instance, we're using copper piping. So 40% more copper piping is required if we were to use the industry standard sizing versus the taking the liberties on the right sizing side of things. So this is cost impacts to the project and environmental impacts when considering manufacturing engineering. So it's the whole carbon footprint, not just what you're paying for on the job site needs to be considered. All right, so I think I left off here. So the problems of the sizing impacts in industry standards. So water quality issues, low residual for disinfectant due to age of water in the system, increased biofilm, which harbors the bacteria, loss of temperature for hot water systems. The more water you have in the system, the lower the flow is, the more we're just losing to the what we call the heat sink of the building. So you're losing that energy in the hot water system by it's not flowing fast enough to get to fixtures. Increased volume of flushing to get the hot water to the tap. So, if you want to take a nice hot shower, you're going to let it run until you get the hot water to you. So the sooner we can get that to you, the less water is wasted there. Going into meter data, this is just a sample of data that we use in, excuse me, in right sizing. So this graph here is just a 5-minute average of a lot of data points that were taken every 10 seconds over the course of one day. So in this instance, the system is sized for 150 GPM using industry standard sizing. So that resulted in a 4-inch hot water pipe, which 150 GPM is 4 feet per second in that 4-inch pipe. So that's staying within the industry guidelines of not going over 5 feet per second on a hot water system. What reality 45 GPM peak in that same 4-inch pipe is 1.2 feet per second. And that's only for this one spike right here. When you get to these areas down here, it's well below 1 foot per second. So this is a lot of information, but it tells us the time and range at the various GPMs. One thing to point out is 99.9% of flow happens below 50 GPM. That's the highlighted areas here. 50% of the flow happens below 15 GPM. So if we're sizing our system for 50 and we're flowing 15 GPM all the time, that's even less flow, under normal circumstances, half the time. So going into future studies, age of water studies is going to be big. It's harder to determine age of water, so we try to reduce the amount of water we have in a system. So the more it's used, the younger it is, if you will. So how long does water sit before becoming non-potable? This guides non-potable water dumping to maintain chlorine residual. We need to determine true usage, the p-values in commercial building fixtures. That'll help us determine, if this bank of 20 fixtures is only going to have 2 fixtures running at any one point in time, we size that main for just those 2 fixtures. Increased data on building water flow metering would be helpful as well. And the more information we can get on that, the better we can dial in the Hunter's curve to right size building systems. And an interesting study would be comparing temperature loss related to increased pump energy. So you have more temperature loss with larger pipe, you have more pump energy with smaller pipe. So where's the trade-off? And that's all I have. Thank you guys for your time.
Thank you very much, Jeremy. With that, as Patrick gets his slides shared, I'm going to give a little introduction for Patrick, our next speaker. Patrick Gurian is a professor in the Department of Civil, Architectural, and Environmental Engineering at Drexel University. His research interests include quantitative microbial risk assessment, decision support for risk management, and regulatory impact analysis. Patrick is the principal investigator of an EPA-funded research project developing decision support for managing water quality in buildings. And with that, I'm going to turn it over to Patrick. And thank you very much, Patrick, for agreeing to present.
Sure. Great. So first of all, big thank you to Raj Singh, who's research faculty and drafted this presentation for me. There are many, many collaborators on this, and we'll just This will be like a quick overview of the research project. So kind of snapshots of different papers, and different authors are associated with different papers. So I didn't try to put them all on the title slide. So here's what I wanted to talk about this morning. First, the question of how should we be managing water quality in building? Try to synthesize knowledge from experts and guidance documents, and then look a little bit about how are we managing water quality in buildings, a survey that we're doing of superintendents and facility managers, and then think about how we could bring these two closer together by providing decision support. So again, really brief tour. There will be links to papers. In some cases, I'm just trying to pique your interest in a paper, and I'll have a link to our ResearchGate site, and that has our papers listed as well. All right, so the first one, I'll talk about this in a little bit of depth. So this is basically looking at controlling opportunistic premise plumbing pathogens, or OPS, and looking at a systematic review of guidance documents and conversations with some subject matter experts, looking at, what do we know, what do we not know, what do we agree on, what do we disagree on. So the basic procedure here was we interviewed 22 different subject matter experts about water quality in buildings, design issues, operational issues, sources of information, and then we identified actually quite a range of guidance documents, but there were 15 that we really went through in the most detail. Again, so trying to identify trouble spots and best management practices. So this table is an example of some of the types of results that we got. So we did just kind of a simplistic, was the feature mentioned favorably or unfavorably? And so we kind of got a list of features that are flags, if you will, that you would want to give people guidance and, be careful if you have these features, or maybe even avoid those features. So for example, low flow fixtures. You can see the SMEs are the first two columns after the title column. So low flow fixtures, then we get favorable and unfavorable mentions from the experts. So out of the 22, almost a third, 7, said unfavorable things about low flow fixtures. Nobody had anything good to say about them. Of course, they do save water, save energy. When we go to the guidance documents, there was much less that we encountered. Out of the 15, 2 had unfavorable. Similar things going on with electronic faucets, with subject matter experts being concerned about them being possibly promoting the growth of opportunistic premise plumbing pathogens. When we got to thermostatic mixing valves, it was kind of a mixed bag. People had favorable and unfavorable things to say about them. If you talk to the experts, it would, just slightly shade towards the unfavorable. If you read through the guidance documents, maybe slightly shade towards the favorable. And I think that continues to be kind of a difficult issue for us to sort out. There are contexts where I think they can work. There can contexts where they're maybe not being well maintained and might be doing more harm than good. All right, looking at temperature recommendations for opportunistic pathogens control. When it came to hot water heaters, there was pretty good agreement that in terms of the set point, different sources of guidance seem to be saying, have that water heater at 60 or above. Then when it came to actual hot water in the plumbing distribution system, there was a little bit of difference with, some sort of being more on the 55 degrees and others saying 50 was okay. Meanwhile, if you go to the concern over scalding, in that case, it's below 43 degrees. At that point, you can have almost unlimited exposure to the water. There's some other guidance out there that says, well, keep it at least, below 49 in terms of scalding risks. You can still get scalded with water at that temperature, but the exposure periods are quite long. So here, I think, again, there's a little bit of daylight between the guidance as far as water in the distribution system for opportunistic plumbing pathogens control, and certainly the well-acknowledged conflict between scald and OPS control. Rashed, who's my graduate student, went and tried to do a meta-analysis of this. He looked at reports from hotels of temperature in the hot water system and the probability of Legionella being detected. And unfortunately, you can see that even at fairly high temperatures, the probability of positive results was reasonably high. So that would be sort of a push towards maybe the higher temperatures, but we do have to keep in mind that it's not just about detectable versus non-detectable. Risk is going to be a function of concentration, we're pretty sure. It might be interesting to see how much this curve would change if instead of being just detectable, if you had the probability of being, say, above 1,000 CFU per liter. Some sort of concentration threshold. There was some suggestion in the data that indeed lower temperatures would be much more effective at controlling levels below, say, 1,000, something like that. But unfortunately, not enough data to really analyze quantitatively and fit this nice logistic regression curve like Rashed could do to the detect and non-detect data. All right, so this brings up the question of how much Legionella is too much? Is any detectable Legionella too much? So this is something that Carrie Hamilton, who I think has spoken to this group, had a paper in Environmental Science and Technology. And the answer, of course, is it depends. There's not really a bright line approach, but just to hopefully pique people's interest a little bit, I'm going to try to throw out a bright line value, if you will. And, you know, again, it depends on the dose response function that you use. But if you're looking at kind of that 1 in 10,000 risk value that has sometimes been used as a benchmark, then you could kind of do the math and map that to 1,400 CFU per liter. But again, lots of assumptions and uncertainty in that, so certainly not proposing that be adopted unthoughtfully. Then Rashed did sort of the same thing with Pseudomonas and Naegleria. So again, there hadn't been too much quantitative microbial risk assessment based guidance in terms of what's a problem versus what's not a problem. So now we've got 3 of these organisms where there's some QMRA guidance as far as how much is too much. Next thing is to flip over from the guidance side to the descriptive side. What are people actually doing? We interviewed 15 facility managers, and then it was just to speed up the process, we were able to do it much more efficiently through a structured online survey. We were able to get similar information via the 2 methods of collection. So we did pool that here. And I'm just going to give a quick overview here. So the interview responses, the medians are shown on the left-hand side. And then the guidance that we were pulling from the literature is shown in the next column over. And everything that is yellow is something that looked like a conflict between what we were seeing in the guidance documents and what we were hearing from our interview and survey respondents. So for example, just to take the first one, the median set point that they reported for hot water heaters was 130 degrees Fahrenheit versus what we were seeing in some of these guidance documents that are cited there of greater than 140 degrees. I'm going to quick jump over to the laboratory side of things. So this is Denier's paper, another grad student I'm working with, and this was a full factorial study of a cold water system looking at different pipe materials, PVC, PEX, and copper, 2 diameters, 3/4 inch and 1/2 inch, and 2 stagnation times, 12 hours and 1 week. And then there was a system set up here in Philadelphia that had chloramine as a disinfectant, and a system set up in Boulder that had free chlorine as a disinfectant. We don't have a perfect experimental design as far as varying the disinfectant. It just wasn't feasible to do free chlorine to dechlorinate and then rechlorinate with the other disinfectants. So we did the best we could. We went to 2 different cities that used different disinfectants. So there is some confounding with potentially unobserved factors there. But in the chloramine system, so here in Philly, we did see that with the smaller pipe diameter, you really did lose residual faster. Whereas with the free chlorine system, we didn't see much of an effect of pipe diameter on losing residual. So the possible story that you can tell behind that would be that the biofilm growth is maybe more important in terms of the chloramine residual loss. Maybe the bulk water decay is more important for chlorine, or is going fast enough anyway that we're losing it, and the interaction with the pipe isn't so important, whereas the interaction with the pipe seemed to be more important in the chloramine system. The smaller pipe you have, the higher surface area to volume ratio. So to the extent that this loss of residual is maybe being mediated possibly by biological processes or just other at the pipe wall, you do see more loss of the residual in the smaller pipes in the chloramine system. Even flushing every 12 hours did not seem to completely get rid of nitrification. It kind of pushed it back to incomplete nitrification. So that was a concern. But on the other hand, the question you also have to ask is the nitrification producing the sorts of problems? I mean, certainly nitrification is, I think, a risk for all kinds of other problems. You have these nitrifiers growing, and you could have a much more active biofilm and get lots of bacteria that you don't want. But we didn't actually see Legionella in that system, possibly because it wasn't at a favorable temperature. We did see some NTM, non-tuberculous mycobacteria. Let's see, but they were actually more common in the system that was flushed more frequently. So we don't actually have a recipe for how to avoid any nitrification in a chloramine system. Unfortunately, we found at least traces of incomplete nitrification under pretty much all the conditions we looked at. So that paper just came out. There's a link to it. I wanted to
Patrick,
go.
sorry to interrupt. You have about 2 minutes left.
Okay, great. So this is just the list of publications. I was hoping that maybe we'd be able to share the slides. People could access them if they're interested. And of course, there's a whole bunch of manuscripts in the file drawer that we hope to have out soon. Where do we go now? I think there's mostly consistent guidance. There are some gaps and conflicts. And some of the guidance, when you get down maybe more to the nitty-gritty level, is scattered a bit across different sources. So we're looking at how we can bring that together into a decision support system. It does seem like a lot of facilities have ops-friendly temperatures in their hot water systems, so there's a potential need for decision support. There's some opportunities for people to be involved. We're always interested in people following us on ResearchGate. We are looking for participants. Our Delphi study is particularly looking for people who sort of meet certain thresholds for expertise and would be willing to do several rounds as in a Delphi study, but each round to about 30 minutes. And you're welcome to join for the first round and then ditch. That's that you don't have to stay for all rounds of the Delphi study. So that would basically be a 30-minute survey, less than 30 minutes for people who meet the inclusion criteria just in terms of publications and things like that. So go ahead, please reach out to us if you have opinions about water quality in building and would like to weigh in on them. And then in terms of the decision support, we're looking for beta testers. That is not as sort of control the process. We're just looking for input from anybody. So everybody is welcome to be a beta tester. So we've got our contact information there if you'd like to volunteer for either both of those opportunities. And then I just want to give our standard acknowledgement in that we were funded by EPA, which we greatly appreciate, and name some of the many collaborators on these papers. So thanks so much for your attention.
Thank you very much, Patrick. And Really appreciate that. And I think our approach will be to just share these slides in a combined PDF, and Bill has brought those together for us. So we'll be sharing that on the Drive side, I believe. Our next presenter is Liliana Latonovich. And as Lily, okay, she shared her presentation. I'll give a little introduction. She was born and raised in Serbia, and after obtaining her first master's degree in 2009, she relocated to the Netherlands, where she obtained her second master's degree and also defended and obtained her PhD. Currently, she works as a postdoctoral researcher at Delft University of Technology and Amsterdam Institute for Advanced Metropolitan Solutions. So with that, I'm going to turn it over to Liliana for her presentation. Thank you.
Thank you very much, Rob. Do you hear me well? Can you hear me?
Yes. Yes.
Okay, great. Great. So first of all, thanks for having me today. I'll talk about water stagnation, impact on water quality, which was a part of my PhD research. Okay, there is no universal definition about safe drinking water, but what we all, I guess, want when we turn on our tap is that we water that is clean, that contains no visible particles. Okay. So what we also would like to get is a wholesome water that is good for our health, and the water that is hazard-free, actually, that has no hazard that could potentially make us sick, either through chronic or acute exposure. Because I did my PhD research in the Netherlands, I will just introduce you how the drinking water chain looks like in the Netherlands. So actually, Dutch drinking water companies, there are 10 of them, they're publicly owned, and they are responsible for abstracting, treatment, and distribution of the drinking water. And they have even their own secret how to do it by applying, for instance, best available sources. And on this screen, you can see that like 70% of the drinking water source is actually groundwater. We also apply very efficient technologies, either conventional or state-of-the-art advanced treatment technologies to purify water up to the desired level. We distribute water without residual disinfectants, so no chloramine, no chlorine, but we do that by actually producing so-called biostable water. So that is water that contains less than 10 micrograms of AOC, assimilated organic carbon per liter. We also maintain low, which is like less than 3%, and we optimize and maintain the distribution network, and we also apply statutory monitoring. And Dutch drinking water is of top quality, and that is also shown by international research. Here's a nice article published in Nature, How Do You Like Your Tap Water? But despite this, opportunistic pathogens are more often observed in premise plumbing water samples than in samples from drinking water distribution network. So that actually points out how important premise plumbings are. So by the time we started our research, there were already some studies showing that overnight stagnation could induce microbial activity in stagnant water. But at that time, it wasn't clear actually how temperature or the extent of residence time or stagnation, actually, what is the impact of that. So our research goal at that time was to assess the extent to which the two surrogate indicators for water quality, temperature and stagnation, contributes to the alteration of drinking water quality in premise plumbing. So to do, to answer our research question, and we had to do something, and the easiest way was to actually build experimental setups. Here is the photo how our experimental setup looked like. So actually we built two premise plumbing systems. One was resembling premise plumbing in typical Dutch house. The other was built so we have extra piping, for instance, for fire sprinkler application. And we published 2 papers, one in water research and one in water, on the experimental findings. So how we actually mimic the household water use. We generated 365 demand patterns. So each of the tap, we had 11 tap in our typical Dutch house plumbing system. So each of the tap had unique water demand pattern every day throughout the experiment. And we controlled and acquired data using LabVIEW software. In terms of, we conducted long-term experiments, which meant that we sampled fresh water at 10 o'clock in the evening. We let it stagnating for 10 hours, and at 8 o'clock in the morning, we would sample stagnant water for kitchen and shower tap. We applied certain methodological measurements. So we measured HPC, heterotrophic plate count, ATP, adenosine triphosphate, flow cytometry, cell count, copper, zinc, TOC, Legionella, and Aeromonas. We also performed some short-term experiments in winter and summer, where we left water to be stagnant in our system for 40 minutes, 4 hours, up to 168 hours. And at the end of our experimental run, we also extracted biofilms from kitchen and shower taps, but this I'm not going to explain you further today. You can refer to our published papers. So actually, as I mentioned, we measured copper leaching. We assessed copper leaching during overnight stagnation. Well, we saw that there is a considerable amount of copper leaching from copper pipings, and that was already known. But what was interesting to see that there was quite a huge difference between stagnant water kitchen tap and stagnant water shower tap. So that was also not known before our experiments. And the same goes for zinc leaching from brass elements. In fresh water, we had, let's say, 20 micrograms per liter, then around 70 and even up to 90 on average we get from kitchen and shower tap. And it was also nice to see that it behaves similar to the copper, and we concluded that the difference between those two taps is based on microclimate effects in a house, because our kitchen tap was on the first floor. On the second floor, we had a shower tap, and on the second floor, we always had at least 1 degree of higher temperature around the piping. We also assessed the microbial water quality of stagnant water by using heterotrophic plate count, and it was interesting to see that actually there was a tipping point when looking into the change in microbial parameters for HPC, for instance. And we see that if temperature of water was less than 16 degrees, then we would have regrowth in our premise plumbing. And if the temperature was higher than 16 degrees, then we would have die-off, actually, of heterotrophic organisms in our premise plumbing. And the same goes for flow cytometric cell countings. ICC stands for intact cell count. And we saw the same pattern, but only the only difference was in terms of temperature. Tipping point in here was around 17 degrees. And I will just show you differences in ATP concentrations driven by freshwater temperature, which was 17 degrees, as I mentioned, or in Fahrenheit is around 63 Fahrenheit. So if freshwater was higher than 17 degrees in temperature, that we would have a decrease in microbial activity, and vice versa. If we would have freshwater temperature lower than 70 degrees during winter time, for instance, season, then we would have an increase in microbial activity. It was also interesting to see that there was kind of a difference between kitchen tap and shower tap, and that is probably because of the content of copper that I already mentioned, because copper is toxic to bacteria. So to round up, what were the presentation takeaways? Water stagnation promotes leaching of copper and zinc from copper pipes and brass fixtures, but we see the difference between different pipes within the one household. Microbial quality parameters of stagnant water might depend on fresh water temperature, and that is in unchlorinated system. So just to put accent that there is no residual disinfectant in the Netherlands, no chloramine, no chlorine. So flush your tap truly before using water, either for drinking or cooking processes. So.
No, thank you very much. Really appreciate that. And our final presentation is going to be by Tim Bartran. And Tim's got his slides up. Introduction. Tim is a research engineer with ESPRI, the Environmental Science Policy and Research Institute. Tim's current focus is on microbial and chemical risk management for building water systems and fostering partnerships between water suppliers, water customers, and the public health community. And again, thank you very much, Tim, for agreeing to present.
All right, quick sound check. Can you hear me?
Yes.
All right, sounds good. Thanks for the chance to talk. I'm going to be talking about building water quality monitoring. I'm not going to be talking about a critical part of monitoring, which is the water quantity or the hydraulic monitoring. That's not because it's unimportant. It's simply not part of the presentation today. So thinking through, as I was thinking, all right, what would this group want to know about monitoring, given that this is a modeling group, and here is, in my mind's eye, the connection between the monitoring and the modeling. It goes in both directions. Monitoring is a data source for, I'm using the word conditioning, parameterizing, whatever you want to call it, the water quality models, and also for validating the models. Sometime down the road, we will be developing as a community the models, and we'll need to validate those using some data. In the other direction, the modeling can do things like identify optimal water quality monitoring locations. As everybody knows instinctively, and you'll see later in the presentation, there are a lot of choices for where to monitor. You can't monitor everywhere. So having modeling assist us in addition to expert elicitation on where to monitor would be a great application for modeling. And we can also extend the monitored location results to non-monitored location results in times. The purposes that I come up with for water quality monitoring, they are for process control and operational monitoring. And Jason did a very nice introduction to these, and I'll talk about them, in some detail, a little bit more detail than Jason did. But the purposes are to verify that the controls that are in the water management plan are in place and operating as intended, and then to validate that the controls are achieving their intended goal. And based on Jason's presentation, I'm going to modify my approach and talk not just about monitoring, but about surveillance, because the public health surveillance, in addition to the Legionella monitoring, really gives you that whole package of knowing whether your controls are adequate or not. Event detection, it's almost a certainty that somebody on this call, or at least in the community, is thinking about event detection with respect to monitoring. There are efforts underway to do online or real-time monitoring in buildings, and why would you do that if you didn't have something to do with the data? And that's probably going to be event detection. Event detection could be something like detecting building water supply events. They could be detecting events within the building. Some bad effect of unexpected stagnation, as Patrick mentioned. Kind of detecting the onset of nitrification. Those would be examples of event detection. And then this isn't exactly monitoring. This is environmental sampling. But incident response is going to be another application for monitoring, and that would be things like confirming that flushing achieves target water quality. William Rhodes recently put out I guess it's a guidance on flushing after stagnation, and there is monitoring involved in that, or to conduct follow-up monitoring after a Legionella positive sample or a case or outbreak. So real quick, process control, operational monitoring. Why are we doing this? We're going to assess the performance of individual control measures and make sure they're working effectively and as designed. And we're going to validate the process controls are achieving their goal. Key parameters. One is, this is sort of in the surveillance, not monitoring area. System inspection and integrity, sanitary surveys, maintenance logs. Those are things that need to be monitored. Water use and water flow, temperature, disinfectant residual, those two being that water use, temperature, and disinfectant being the main tools in our arsenal for especially Legionella. And then other potentially indicators of biological stability. Liliana's presentation showed a really nice use of ATP and other measures of biological activity as nice indicators of water quality and water degradation in building water systems. Where do you want to monitor? All of the control locations. So rewinding to Jason's presentation, there are control locations that are chosen based on either the ability to control water quality or based on the likelihood that there is trouble, a chance that you might be growing, for example, Legionella in a location. You want to monitor at the building entry point and the water heater discharge and return, and in sentinel locations, distal locations. And how are you going to monitor? This is more of an art than a science, but the WHO advises that monitoring frequencies are selected so that you can get your corrective actions in place in a timely fashion. And there's a lot of interpretation that can go into that. Going on to validation and Legionella pneumophila detection and enumeration. I'm going to start the discussion about Legionella with discussing two methods or two kind of big picture approaches for looking for Legionella. There are culture methods and molecular methods. And apologies to the microbiologists on the phone. This is a little bit basic for you, but I think helpful to go through. Culture methods count the live, viable, and culturable organisms. So these are the organisms that we know if somebody is exposed to them, it increases their risk of illness. The results of assays are directly indicative of health risks, and they can also be compared against standards and criteria that are culture-based. And to the best of my knowledge, all of the criteria right now for assessing water quality, for judging whether you are validly controlling Legionella are culture-based standards. That doesn't mean that's going to be true forever. However, that's just the state of play right now. To culture methods, there are molecular methods, and this is the qPCR or other techniques that are used. And what they measure are concentrations of genetic material from live, culturable, live, and non-culturable. And this is important because Legionella can become non-culturable, but that doesn't mean that they're not a risk or they're not a hazard. But you also can detect the genetic material from dead organisms. And I'll quote, if genetic material is found, it came from somewhere. And I say that because using results from molecular methods is a great way to, it's a different way and a valid way to assess what's going on with respect to Legionella in a system. There are some people who think that culture methods really have to be the technique that you use. And I've seen successful use of molecular methods for monitoring for Legionella. The molecular methods are potentially more sensitive than culture methods, depending on how you run the assay and the water quality. And the results of the assays have been used for many things, but as yet they can't be compared against standards and criteria because those standards and criteria don't exist. Where do you monitor for Legionella pneumophila? The CDC toolkit, which is a great resource, and we heard about earlier, says if the team decides to perform validation using environmental sampling for Legionella, first of all, you have to have this as part of a comprehensive monitoring plan. And sampling plans are unique to each facility. They're a nice quote, I think she originated at Shantini Gamage from the VA. If you've seen one VA hospital, you've seen one VA hospital. Each building, as other speakers have said, is quite different from the others. So you have to tailor your monitoring, your Legionella monitoring for the specific features of the building, and that includes the population served. And there are a number of other criteria that you might use that you can find in the CDC toolkit. An example of a sampling plan. This is courtesy of my colleague Tom Hargy. Hopefully, I've taken all the identifying features from this diagram. You can see that for a single floor of a healthcare facility, we have a number of sampling locations, and those were selected. They include the point of entry. They include water heaters and hot water returns. And then they include locations either where there are critical exposures or these sentinel locations where we want to know, for example, at the very end of the run, what the water quality is. And I asked the community, could and should modeling reduce the reliance on expert judgment and help us develop better monitoring strategies? I think that's a real good opportunity. A little bit more about Legionella pneumophila. You need a lot of data to make sense of Legionella counts. And again, CDC has given a pretty nice list of other descriptive data that you need to make sense from the Legionella. And you'll see in the next slide what those data look like. Another thing about monitoring, before you start monitoring for Legionella or other OPS, the opportunistic premise plumbing pathogens, you need a formal plan to do what to do when, not if there is a positive sample. You need to establish a priori trigger levels and actions and responses, and super critical, you need to have a communication strategy and communication tools. That is, the actual emails and texts and strategies like a chain of command. You have to have those in place before you start monitoring for Legionella, because it's incumbent on you to tell stakeholders what you find if you should find Legionella. So in practice, I apologize. This is kind of an intentionally busy slide, but in practice, what you see in Legionella monitoring, I have on the left-hand side for one particular location the measurements that our team did in I think this was a healthcare facility. And on the right-hand side, we have just two monitoring events, and you can see the positivity and negativity for culture Legionella pneumophila. And there is a lot going on here, and it's not a simple look at the numbers, see if they're positive and negative, and do some corrective action in the control system. You have to analyze the data. You have to understand what's going on in the what the layout is and what's going on in water use and so on. You'll see that the field measurements that we took in this particular location, we looked at temperature using a couple of different probes, total chlorine, and we had the luxury of looking specifically at monochloramine. And we looked at nitrite. You can see that we had a chloramine. The supply was chloramine here. Turbidity, pH, and conductivity. And then on the microbiological side, we threw the kitchen sink at this, and we looked at Legionella using a culture technique called Legilert that we find very useful. And we also looked at some of the other opportunistic pathogens. And a word to the wise, there have been some events in which others have looked at opportunistic pathogens and essentially panicked when they found, for example, not super high concentrations of Pseudomonas aeruginosa. And you have to really be prepared if you're going to monitor for these other parameters to know what to do should you find them. On the right-hand side, you can see that this facility is making progress. The orange cells show positive Legionella pneumophila. None of the concentrations was particularly high at this facility, so they're just refining their water management plan. And the green cells show negative. And you can see that throughout the system, on samples collected 1 year apart, there was a significant reduction in the percent positive. There's one case in which a negative location went to positive, and that certainly deserves scrutiny. All right, that's a quick run through monitoring. I have a few key resources at this slide, and no monitoring presentation would be complete without invoking Lord Kelvin, and if you don't monitor it, you can't control it. Thanks, everybody.
Thank you very much, Tim. That was very nice, and thanks very much to our other presenters today. If you have any additional any additional questions, or know of folks that want to be, on our distribution, please have them contact Jun-Suk Lee, and I put on the screen now his email address. He's our task committee chairman. If you have any follow-up questions to this webinar, please send them to Jun-Suk. So far, we've completed, I believe, 6. This was our 6th webinar. The next one is on instrumentation. And Bill, I believe, will be heading, will you be heading that up, Bill?
Yes.
Yes. And that's scheduled for December 3rd. So we're skipping it November because of Thanksgiving and whatnot. And then we'll follow up with 3 more in January, February, and March. And then the instrumentation one next month by Bill will be specifically Thursday, December 3rd, and it's the same time slot of 10 to 11:30 a.m. Eastern time or New York City time. And I think that's all we had, unless Jun-Suk or someone else from the committee perhaps has anything else to say.
You covered everything, Rob. Thank you very much, and thank you for all the speakers and then attendees. I appreciate it. Thank you very much. Yes, Rob.
Yeah, thanks everybody, and thanks again for attending. Really appreciate it.